So to start off this problem, I'm going to draw a figure to represent a pool. So we have a rectangular prism. This is our water. This is our length, this distance right here, and this is the width for this distance right here. That's very messy. This is the width right here. And this pool has a depth of d. And so we need to derive an expression for the force necessary to hold back a wall of a rectangular pool of length L with W and with a fluid depth of d. And so we need to derive that expression from the expression we got from last problem. And so we need to figure out the pressure force at which the water pushes against this wall right here. So we only need to focus on the shorter face. So the longer face really doesn't matter in this problem. And we're going to set the direction, the positive direction, downwards. And we're going to represent height with just h. And the height of the surface, the height of the surface of the water is just going to be 0 in this case. Remember, there's a depth of d. And there is going to be multiple points of contact for the force involved. So there's going to be multiple forces pushing against the wall right here. And each of those forces, they're going to be, I don't know the symbol for pointing outwards, but there's going to be forces pointing outwards out of the page. And that force is going to be dF. So I'm just going to, there. That's dF. It's going to be pointing out of the page. And the depths will also vary. We're measuring it from different points of height. And we're going to represent all those individual points of height as dH. Okay? So since we need to find the force of the water pushing against the wall, we're going to form a derivative for dF. And that derivative, or sorry, integral, not derivative, that integral will be the pressure times that by the surface area of the wall. Now, since we solved for the pressure in the previous problem, we can plug that in place of P. And PG, those are constant. So those stay outside the integral. H will remain inside the integral. And then we have dA to worry about. And so dA in this case would be the width times that by dH. So width times dH, because again we're taking multiple points of contact in the figure. So width times dH will represent the surface area. And we can also take out the W, because that also remains constant. Oops, I didn't take out the W. That will remain constant in this problem as well. H times dH. Right? So before we can integrate, we also need to find the bounds involved. So, again, since this is the starting point from this point, right, the first point will be 0, since we established that the surface of the water will be 0. And so we need to travel towards the bottom, and this full length right here will represent the bottom of the pool. And so we'll go from 0 to a depth of d. So d will be the new bound. So now we can integrate. So PGW remains the same. We integrate h dh. In doing so will give us h squared over 2 with the bounds 0 and d. And getting that, or plugging those values, will give us d squared over 2 minus 0 squared over 2, which that's just 0. So that simplifies to rho GW times d squared over 2. And so that will bring us to our final equation or expression. The force pushing against the wall of the pool will be equal to rho GW times d squared, and all of that over 2.